Next speaker is here in the audience in person, Sébastien Bossu, talking about generalizations of the Carr-Madan spanning formula. Thank you.
Thank you.
No.
Can you hear me?
Okay. I thank you certainly for having me at this conference. I want to thank the FRE department, the scientific committee, for selecting my presentation. And we've been hearing a fair bit already about the Carr-Madan spanning formula. This is some of the most recent work that I've done jointly with Peter and Andrew on generalizations of a spanning formula. I've known Peter for more than 15 years. And I was very saddened by his loss, and he really was a man of models and also a role model for quants. So I think we all terribly miss him. In France, where I'm from, we have this saying that in life you should give a lot to receive a little if you want to receive a little. To me, Peter was very much the embodiment of this nice saying, because he gave so much of his time and ideas and so on. And you could say it's a little bit of a wise man, a wise person, no arbitrage principle. In finance, we like to give a little and receive a lot, but probably as a maxim for how you want to behave and do your research and conduct your life. Generosity wins in the end. So certainly he's been a tremendous source of inspiration from that point of view. Yeah, let me get started. So I just click here. Okay. And then the clicker is, I can use this. Okay, thank you. Okay, so a great deal of mathematics is about breaking down complex structures into simpler ones. And then we apply the totum summa partum principle. The whole is the sum of its parts. And in fact, Taylor's series is a famous, powerful tool to break down complex functions. I mean, complex in the sense of, giraffe functions, complicated functions, into a sum of simpler power functions. In the Carr-Madan spanning formula, as we've already covered, breaks down essentially any single asset European option, especially the law contract, as a weighted sum of cash for contracts and vanilla options. And if you want to just write it in a semi kind of journalistic way, you could say, European payoff is, this sum as wrote here. The sigma here is actually an integral, as we know. But, essentially, you can replicate any European option using more basic options, the call and puts. And most successful application, of course, is the law contract, and that led to the VIX. So after, I guess, going through again the spanning formula, maybe I'll go a little faster since it's been covered very brilliantly by Jim and many others already. But I want to present these generalizations to two classes of multi-asset European options, especially. And this is a very novel result. When I was in industry, I felt like, well, the Carr-Madan spanning formula, this is very nice. We can replicate anything with vanilla calls and puts, but only for a single asset. And it seemed impossible for multi-asset options. And I'm very proud to report that it actually can be generalized with some assumptions, of course, to multi-asset options. So one big class is dispersion options. I'll define them. Not everyone is familiar with them. And then another class is European options with homogeneous payoff, such as best of. And the main mathematical tool for breaking down the multi-asset option as a sum of basket vanillas, that's what I'm using for verification, is known as the Radon transform. And it's also used, as it turned out, in medical imaging and other fields of engineering to reconstruct, for example, the slice of a patient's brain. And the Radon transform is closely related to the famous multidimensional Fourier transform. And I knew nothing about Radon transforms before I got into this line of research, and it's been quite a journey, but very fascinating one. So I guess I would just add that when a pure theorist may be satisfied with maybe an abstract general solution, leaving out the technical details, we actually tested the theory with relevant applications, and we derived first time explicit solutions. And I guess there's a little image here to remind us that the devil is in the mathematical details very often, and certainly in this line of work that's been the case, but it's been really fascinating as well. So after a brief introduction, I'll go maybe a little faster into the Carr-Madan spanning formula and showing also alternative proofs. And then talk about generalization to multi-asset options. And then hopefully we have time for a few application results to show you. So I mentioned dispersion options. That's another of my early pet themes, dispersion correlation. And these are options, sophisticated options, typically between a hedge fund and a bank. And on the term sheet, you can see that, do I have a, yeah, so you can see that it's on like 5 underlying assets. In these cases, these are various shares. And then the payoff is the max of 0, and then dispersion minus some strike, and the dispersion is the average of absolute returns to maturity, gross returns of the shares. And so if the shares don't move, then the dispersion is 0. If the shares move a lot apart from each other, I guess, then you get a huge dispersion, and it's a rare kind of exotic option that is short correlation. So the banks kind of like to sell this product because then they can buy back correlation, when most products are actually long correlation, and the banks are kind of accumulating correlation risk as a result. So that's one particularly sophisticated type of option that's actually hard to price, and unexpectedly the line of research shows that you could at least theoretically price them with vanilla basket calls. Some other notations that already been encountered. So the max of 0 and t, I like to call it here the RAM function, so positive part. So you recognize the building block for a call option. And if you take the derivative against t, you get the step function, 0 to the left and 1 to the right. And if you take the derivative of a step function, you get the Dirac delta function, which is not really a function, a generalized function, a distribution, which is 0 everywhere except at the origin where it takes an infinite value, right? So, and so let me talk a bit more about, the original source of inspiration, the Carr-Madan spanning formula. Again, so we get this formula we've seen before, the payoff, arbitrary payoff, European payoff is decomposed as a sum of cash forward contracts and a bunch of calls and puts on a continuum of strikes. And these are pretty standard notations, so I'll skip that. So the original proof, as Jim has shown already, I'll just give you a slightly different version where I take the split between calls and puts as 0, meaning that I'm only spanning with calls. That just simplifies a little bit, but you get the same ideas. And then the property that Carr-Madan used here is the shifting property of the Dirac delta function, which is that since the Dirac is 0 everywhere except at the argument, when the argument is 0, then essentially what you get here is you recover, if you integrate against f of k, you recover f of st, right? And then you integrate by parts, and you do the calculations, and you integrate by parts again. And after all kinds of calculations here that are pretty straightforward, you end up with the Carr-Madan spanning formula. Another proof that's found sometimes too is you can start with the right-hand side. So f of 0 plus f prime of 0 st plus the integral here of f second of k, and then the Cole payoff. And for k greater than st, the Cole payoff is 0. For k less than st, the payoff is simply st minus k. So this integral that goes from 0 to infinity is actually not really going from 0 to infinity. It stops at st. And then we can get rid of a plus here, and then you can integrate by parts. And after all kinds of calculations and simplifications that are very easy, you end up with the right-hand side being the left-hand side. So that's a sort of easy way of proving the formula without delta functions, direct delta functions. The proof that I like best shows us the sort of fundamental nature of a Carr-Madan spanning formula. And that's basically starting with a Taylor series, first order Taylor series with remainder and integral form. I actually have not seen the remainder and integral forms during my studies, but I encountered that, on Wikipedia pages or some other calculus reference. And so, the Taylor series is, we recognize the first order terms, and then the remainder can be expressed in exact form as an integral. It takes this form. And so then you take x equals t, a equals 0, t equals k, and you end up with this expression here, the integral from 0 to st, and then you have st minus k. And as I argued just the slide before, this is the same as the integral from 0 to infinity, and then the Cole, the plus part that appears here, and you're done. And so that's my kind of favorite part, way of showing it, because it shows the connection with Taylor series. And this is important to have, of course, an integral that goes from 0 to infinity, because that's when you actually have a Cole showing up. And bearing in mind that you may want to take expectations. If you have to take the expectation of an integral where the bound is the random variable, that can be difficult to calculate, right? But thanks to replacing the upper bound with infinity, we get an easier way of doing it. So I think this is all quite fascinating. Jim already, I think, gave lots of details about the log contract. So I think that I'm going to probably skip, but this is the important application of the Carr-Madan formula. And again, the log contract, I should say, was introduced by Neuberger in 1990. It pays the log return to maturity of the underlying asset. And it's interesting because it has constant dollar gamma. I have an early paper from my days at JP Morgan that shows kind of empirically how that's the case. And this is really good, useful for variance swaps and the VIX and all of that. The log contract, of course, does not trade. And the solution to this practical problem is saying, well, you can actually replicate it with calls and puts. That's where the Carr-Madan formula come into play. And so, again, you get this way, a replication strategy for the realized variance, 1/2 of sigma t square integrated, and that would be as a constant position in 1/s in the underlying asset until maturity, and then, forward contracts, calls and puts. So this is covered already. It's usually well known from, I'm sure, most of the audience. So just wanted to go through that. And then actually the first generalization, which is still on for a single asset, is kind of framing this in integral equation theory and functional analysis. So this is work with Peter and Andrew that was published in 2021 in Quantitative Finance. And so we generalized this kind of problem by saying, okay, I want to replicate my exotic payoff, maybe the log contract, with a combination of cash, a certain quantity to be found of the underlying asset, and then a continuum of maybe other kind of options, an entire family of options, maybe option strategies, especially are interesting, and then I want to find the quantity phi of these options, perhaps straddles or butterflies, that would replicate. And it turns out to be an integral equation. And so solving for phi has its kind of own challenges and methods, but you can generalize this way to not just calls and puts, but any kind of kernel G that is a family of payoff of options. And so we solved it for the straddle, also for butterflies, gets really a little hectic there. And so that was one nice way of generalizing to replicant options that are not just vanilla calls and puts. The really amazing generalization that we worked on then is for the multi-asset case, a lot more challenging kind of integral equation problem. So this was recently published for the dispersion options in quantitative finance, and was a featured article. So I thank Jim and Michael Dunster for featuring this article, and also my other work on homogeneous payoff for best of and so on is going to appear in Applied Mathematical Finance. So really fresh off the press. And so now what we have is, remember Carr-Madan, we replicate, a single underlying asset type of option with calls and puts. In our approach, we want to replicate a multi-asset option. So we have x1 to xn being the asset returns or asset ratios, price ratios. And then you want to replicate that with cash forward contracts, and then a bunch of vanilla basket calls, which we decided would be the sort of most practical, so to speak, family of multi-asset options that we could replicate with. And then we want to solve and find the quantities of these vanilla basket calls. So now we have a multiple integral, and we are spanning not on strikes, but we are spanning on the weights of the assets in the vanilla basket. And so we have a multiple integrals spanning a continuum of Rn. So that function here is the payoff of a vanilla basket call. So that's how the problem is phrased. It turns out that it's kind of not an easy problem to solve, and that was solved using the Radon transform. So benefits of this generalization is that, as a result, any multi-asset European option can be priced with the same model that is used for vanilla basket calls. So, vanilla basket calls, any bank can price them for any kind of weights typically. And so if they're happy with their model, then in principle, the same model should also correctly price the multi-asset option. This is a little bit counterintuitive and counter practice, but in theory, under penalty of arbitrage, that's what you should do. There's also practicality here. It may help identify approximate static hedges. I'm working a little bit on that now with 2 PhD students of Stéphane Crépé. And so that's a benefit. Limitations are similar to Carr-Madan. You would need to discretize in practice, in order to have a finite number of options. The weights could be negative in this approach, so actually to end up with also spread options, spread of baskets. The vanilla basket calls are OTC. That's the major limitation, is that we don't have as much market information. The banks have plenty of information. They exchange privately between each other about pricing of vanilla basket calls, but the public usually doesn't have access to that. However, within the multi-asset exotics, my argument is that the vanilla basket calls are the sort of most liquid in a otherwise fairly less liquid category, of course, compared to single asset options. Another practical challenge here is that some quantities phi could be infinite, and that's typically resolved with integration by parts, especially that works well in 3D and 2D. So we solve this for 2 classes of multi-asset options: the standard dispersion options, which is kind of a little bit similar to the spreadsheet, the term sheet I showed initially. And in this case, the payoff is a function of one variable, and the one variable is the L2 norm. And in practice, it's L1 norm for industry traded dispersion options. For mathematical reasons, we choose the L2 norm, of course, the 2 are related. So this is the quantity finance paper that was just published. And then it turns out that you can also do that with more arbitrary types of payoff. One restriction I used is with absolutely homogeneous payoff that works for best of and worst of and a bunch of other multi-asset options. But I can say that I'm pretty convinced that basically any multi-asset option can be replicated as well using vanilla basket calls. And so work is ongoing for a sort of a complete theory here. So what does the solution look like? Unfortunately, we no longer have a simple sort of second derivative that the Carr-Madan formula offers, which is straightforward. And so what we do get is we get the inverse Radon transform of the second derivative, we find that again, of the payoff function against some parameter k that is found on both left-hand side and right-hand side. And so this Radon transform, notation, our script inverse. I'll just explain, shortly what it is. And the proof is actually for the sort of general theoretical solution is pretty straightforward. We want to find phi such that, the left-hand side is equal to essentially this multiple integral here of vanilla basket calls. We differentiate twice against k, and then we find that the REM function becomes a delta function. And now we're integrating over Rn, and the delta function is activated when the sum of Wixi is equal to k, which is a hyperplane. And this is the definition of a Radon transform. Therefore, we have left-hand side equal Radon transform of phi, which we are looking for. And as a result, the solution is going to be the inverse Radon transform. So that's the easy part. The theory is the easy part. The hard part is how do you calculate that? But let me talk just briefly about the inverse Radon transform in 2 dimensions. So just give a little bit of an intuition. So let's say we have a solid that is this black rectangle here. And then, we have, just like in medical imaging, we have a ray that would go through the solid. And so on the other side, on the axis, there is I guess a receptor or some kind of device that measures the mass, the sum of masses that the ray goes through. So when there is no mass, the ray goes through here. There is a 0 reading, and then there is here maybe a 2 reading, and then you do that in also the other direction, and then you have a 1 reading whenever the ray encounters the solid. And from that information, just like forget about the solid, and then you back project the information from the y-axis that gives us this shaded area here. You back project the information for the y-axis, which is a little lighter because we only have 1 instead of 2 as a reading. And at the intersection of these 2, you find the solid. And so that's how it works for medical imaging. And this is a simplified case where we're only dealing with a rectangle. If we were dealing with a more complex kind of shape, we don't do that just in orthogonal directions. We do that in every possible direction around the clock. So this is, the Radon transform has been studied and used for decades now successfully. We should all be grateful to Mr. Radon for the fact that we can have this wonderful technology of seeing what's inside our head without splitting it open. And so the inverse Radon, so what would happen in an MRI, you would get this kind of signal on the screen, and that looks like a beautiful piece of art. But if you take the inverse Radon transform, you recover the patient's brain image. So that's, I think, what an amazing already application that was found. Turns out there is an application in finance. It's a little bit more difficult for our problems because typically we need to use generalized functions and so on. So we encounter not like a bounded image, but a potentially infinite number of values. So let me show you the one case that I call the Mexican hat, because it's a little bit like a straddle. So the payoff function here, it doesn't trade, but mathematically it's nice because it's bounded and smooth. And so we get like a nice solution, closed form solution. So if I'm trying to replicate this function of 2 variables, 1 minus the exponential of the sum of squares of x1 and x2, then, so this kind of, Gaussian without correlation. So this would be the payoff I'm trying to replicate. And I can do that as a sum of vanilla basket calls multiplied by a certain quantity. And, after calculations, we showed that, we have in closed form a solution phi that depends on the radius of the weights, W1, W2. And if you just map out the graph the solution, you get another kind of hat, which looks like, I don't know, an American hat, a clown's hat, I don't know, but some other kind of hat can kind of beautifully. And it's a nice solution because it's all bounded and smooth and so on. It involves a special function, Dawson's special function, but it's available in closed form. And so it's kind of, certainly something that amazed me is that you could replicate something as complicated as this type of function. Well, maybe it's not that complicated, but anyway, you can break it down as a sum of vanilla calls inputs in those quantities phi that I showed. Now, the more relevant kind of applications would be, for example, a dispersion call, as shown in the term sheet in introduction. So in this case, the solution is a derivative of a delta function. So a number of people say, "Ooh, what is that?" So, don't fret. What you do is that you do integration by parts in order to recover another decomposition. So in the end, what you get is that, the dispersion call. So that's the L2 norm of the asset prices minus some strike positive part is going to be a sum of vanilla basket calls. It's a constrained sum that is on the sphere, actually. So the radius of the weight has to be 1. And it's a constant quantity of them. And then you have a short position in binary basket calls. So you could say like a limit case of a call spread, a basket call spread. And so you get this other decomposition here that shows, that if you now, this is arbitrage enforcement. So if you want the price of your dispersion call, then all you need to know, maybe a lot already, but you need to know how to price these vanilla basket calls. But anyway, so if you are happy with one model to price the vanilla basket calls, then in theory, you should use the same model for dispersion options, which again is something that many dispersion traders would be a little scared about. But this is so. I think if anything, it probably invites us to do a lot more research on the pricing of vanilla basket calls. But anyway, there is this consistency to be had between these two classes of instruments. The standard dispersion call in dimension 2 is going to be a little bit more complicated type of solution. In some sense, it looks nicer because it's not like a delta prime function or something like that, but it's actually a little treacherous because this is a non-converging integral. So then, immediately people say, well, what did you smoke? What is this? And it turns out that you need to regularize. So there's a whole theory that I kind of learned on the fly on integral regularization. But it's a little bit like Cauchy, integral and things like that. So and again, you can do things a little bit better by using integration by parts and so on. But so it is possible also in 2 dimensions. So one fascinating aspect of this line of work is that the odd dimension is simpler than the even dimension. So the even dimension has a Hilbert transform added to the odd dimension case, and so we get more delicate kind of solutions in the end. How much time do I have? Oh, we are over already. Oh, I'm sorry. Okay, I'll stop here. I'll just mention just one thing, which is that the Besov call is also replicable, and we get again a little bit of a tricky integral. So essentially, again, my strong belief here, and I'll keep working on that, is that any multi-asset European option can be replicated in the spirit of Carr-Madan. I think it's a nice way to honor his legacy to keep working on this topic. So thank you very much.
Thank you so much. Luckily, there is a coffee break afterwards, so it's okay to overrun by a couple of minutes. We'll take one question if there is, of course.
thank you, Sébastien, for this beautiful talk. I mean, there is no way we can stop admiring the beauty of this Carr-Madan formula. And just from Taylor's expansion to this magnificent result that I modestly had the opportunity to use within an old company, but that's another story. Going to multi-assets, what are the assumptions you need to make on the assets in terms of correlation or whatever, variance?
Thank you. Yeah, thank you very much. I agree with you. This is an amazing result with Carr-Madan, and I like to think that this joint work with Peter on extension is also another amazing result. So this is a really good question, because actually I only work with payoffs. So we don't need any assumption prior to state this result. There's no correlation, there is no probability. We're not allergic to probability. There is an application where we find an extension of a Breeden-Litzenberger, which is very much related to Carr-Madan. And so we have another expression involving the Radon transform in order to recover the multivariate joint distribution based on prices of vanilla basket calls. But we don't really need, I mean, this is all payoff related, so you can have anything you want. The restrictions I had is, one is, we had payoff that are dispersion payoffs, so, only payoffs that are single, function, univariate function of the norm, and otherwise absolutely homogeneous payoff. But this is for technical reasons, and, there's a way to essentially get the same solution for any kind of payoff, but I still have to work out the details. So.
Thank you.
And a brilliant way to end for a quick coffee break. We'll be back at 3:45, 3:45. Thank you.